Morning. Uh, Time for us to get started. So, any questions about what we discussed last time? In our previous lecture, we were looking at sensitivity analysis and how to study changes in the objective function coefficients, and also how to study or make analysis and get insights when we change the coefficients of the right-hand side of the constraints, and we look at the sensitivity analysis from the point of view of the graphical point of view, in which we discuss a problem with two decision variables. And then we extended the analysis to look at problems with more than two decision variables. And we, for those type of problems, the sensitivity analysis, the graphical sensitivity analysis cannot be done, or will be kind of difficult to represent by hand. So we transition to the algebraic sensitivity analysis for problems that have more than two decision variables. We look also to the case in which we have changes in the right-hand side of the constraints and changes in the coefficient of the objective function. And the last thing we did in that lecture was to look at the report generated by Excel. So if you solve a problem using Excel, you can get the sensitivity analysis report. And we touch on how the report generates the coefficients for the reduced cost, and also generate the shadow price or the dual price. It also generates the range for the feasibility. So in terms of changing those coefficients for the objective function and the right-hand side, how far can you go to keep the same optimal solution, and then also study the impact on changing those coefficients. So in the assignment that is already posted, you have to look at the report generated by Excel, and then use that information to answer some questions. So make sure that you look at that assignment. Again, not asking you to generate the dual price or the reduced cost or the feasibility range. I'm asking you to use that information to answer questions. Okay, so that will be the assignment that is due on Wednesday. Today, we're gonna transition to a new topic, which is also connected to the sensitivity analysis. So in the sensitivity analysis, dual price, and how that, yes. The assignment or the lecture? Thank you for letting me know, Michelle. It's not there? Okay, so let me fix that quickly. Thank you. Fix that now. Huh, yeah. Yeah. Okay, should be available now. I apologize for that. Thank you. Again, I don't know what happened. The file disappeared for some reason. I apologize for that again. Okay, so as was just saying, the dual theory is connected to what we discussed in terms of the sensitivity analysis. Because what we're going to do now is we are going to look at the original linear programming model. And since we now understand what the dual price and the dual coefficient means, we want to reformulate our original linear programming model into a new problem that will give us answers from the perspective of if I need to make use of my resources, what will be the most efficient way of doing that? What we're going to observe is if we solve this new formulation that is based on the original formulation, you're still going to get the same optimal solution. But the answers are going to be giving us additional insights. The other advantage of formulating the dual problem is that sometimes it will allow us to solve the problem faster, because if you have, for example, in the original problem, you have a lot of constraints, and you reformulate the dual, you might end up with a smaller problem. You might end up with a smaller problem, and then that can be solved easily, and then you still get the same solution, and but in a way that you get solve the problem faster. So we're going to study all those details in this lecture. Let's get started. And again, this is connected to that objective for this class on solving the models for the optimal solution, and also interpreting the model solutions and the inferred solutions to the real world problems. Did the light good, or do you want me to turn off the light so you can see better? Yeah. That's better now. So the objective for this lecture is to understand the concept of duality and also explain how to use the solution of the dual problem in the sensitivity analysis. And the agenda, we're gonna define the dual problem. We're gonna understand what are the primal and dual relationships. And then we're gonna look at the economic interpretation of duality. And finally, what is the post-optimal analysis? So I know I mentioned this already multiple times. Again, this is related to what we discussed in the previous lecture in terms of sensitivity analysis. So let's define what the dual is. So the dual problem is defined systematically from the primal or the original OP model. So let's go back a step. You have a problem, you have defined or you have formulated your linear programming model to make decisions. So now that you have your problem formulation, that's what we call the original problem or the original formulation. And we're going to use that formulation that you just generated. And based on that formulation, we're going to generate a new model that we're going to call the dual. And I'm going to give you step-by-step process for generating that dual problem. The two problems are closely related, and the optimal solution of one problem automatically provides the optimal solution to the other. So even though there are two problems, two different formulations, the optimal solution is going to be the same. Our definition of the dual problem requires expressing the primal or the original problem formulation in the equation form. So we're going to still use these flags and excess variables to define our constraints inequality form. The key ideas for constructing the dual from the primal are summarized in this slide. So first, we're going to assign a dual variable for each primal equality constraint. So for each constraint in our model, we're gonna assign a dual variable. We are gonna construct a dual constraint for each primal variable. So again, every variable that we have for the original problem, now we're gonna generate a constraint based on that decision variable. The column constraint coefficients and the objective coefficient of the j primal variable respectively define the left-hand and the right-hand side of the j dual constraint. The dual objective coefficients equal the right-hand side of the primal constraint equations, and the sense of optimization, direction of inequalities, and the sign of the variables in the dual are governed by the rules in the next table. So these are the rules. So if the primal problem is a maximization problem, the objective function of the dual problem is going to be a minimization. And the constraint type will be greater or equal to, and the variable sign will be unrestricted. If the original problem is a minimization problem, the objective function for the dual is going to be maximization, so it's going to be the opposite. And the constraints are going to be less than or equal to, and the variable sign is also going to be unrestricted. So let's look at one example. So again, the idea is for us to generate a new problem or a new formulation that will help us solve the problem and also going to give us some additional insight in terms of the solution. So I spoke about the different advantages of generating this new model. And then I think the most important one is if we're going to get some additional insights, but also it's going to help us solve the problems faster, especially if you're looking from a computer perspective. So this is the original problem. We have a maximization problem with 3 decision variables, and we have 2 constraints. So one of those constraints is a less than or equal to constraint. So the first thing we're going to do is to set up this problem in standard form. So you see, for the first constraint, we're going to add the slack variable, and we're going to call that slack x4. So one of you asked me last time, why are we no longer using an S to identify the slacks and an X and E to identify the excess variables? Well, at this point, you're already familiarized with the purpose of this decision variable. So the idea of having a different letter was just to make it clear that this was a slack or this was an excess variable. But at this point, you understand the concept. So I can now start using the same letter to identify every decision variable. So in this case, you see we have an X4. X4 is a slack that we are using to make that first constraint inequality. And then for the second constraint, we don't need a slack because we have already an equality. So we are setting up that we're making 0 times X4, which is 0, and then making that equal to 0. So that's the equation form for this original problem. So as we saw on the steps of building the dual, first thing we're going to do is to assign a dual variable to each constraint. Okay, so I'm assigning dual variables are going to be y's. Okay, so I'm going to model those dual variables as y's. So I'm going to assign a y1 to the first constraint and a y2 to the second constraint. Okay, and now using that information, and if I have 3 constraints, then I'm going to have a y3 for the third constraint. If I have a 4th constraint, then I'm going to have a y4 decision variable, and so on. So in this case, since I only have 2 constraints, I only need 2 dual variables, y1 and y2. Okay, so if we go back to these steps, these are the steps that I'm going to follow. Okay, so I already did this. Assign a dual variable for each primal constraint. Now we are going to construct a dual constraint for each primal variable. And then we're going to do that by following this step, the column constraint coefficient and the objective coefficient of the jth primal variable will define the left hand and the right hand side of the jth dual constraint. The dual objective coefficients will be used to define the right hand side of the primal equations, and the center of the optimization will be given by the table that I show you here. So first thing we're going to do, we're going to define our objective function. So as we show here, if the original objective function is maximization, the dual problem will have a minimization objective function. Okay, so we're going to have, since we have a maximization problem, we're going to have a minimization objective function. So to build the coefficients of the objective function will be given by the right-hand side of the original constraints. Okay, so this is going to be 10 times y1 plus 8 times y2. So the objective function for the dual, the coefficients are given by the right-hand side of the original problem, and those are multiplied by the coefficients or the dual variables that we define for each constraint. So this is 10 times y1 plus 8 times y2. And right there you can see we started our formulation, this problem with 3 decision variables, 2 constraints. And right there from the beginning, you can see that we have less decision variables, right? So for example, if we were to solve the original problem with 3 decision variables, you cannot use the graphical method. You will have to go and solve the problem using the Simplex. But in this case, you will see when we formulate the dual, we're going to reduce this problem to only 2 decision variables. So in that case, I can apply the graphical method to solve this problem. And that's just an example of some of the advantages that you can have by reformulating this problem. And at the end, you will get the same optimal solution. Okay, so we formulated the objective function, and now we are going to proceed with the constraints. Okay, so for the constraints, we're going to use the coefficients of the original objective function and the left-hand side of each of the constraints. So for example, my first constraint is going to use these coefficients. My second constraint is going to use these coefficients. My third constraint is going to use these coefficients. And my fourth constraint is going to use these coefficients. Okay, so I'm going to have a constraint based on each of the decision variables, as stated here. So the column constraint coefficients and the objective coefficient, this is step 3 of the J primary variable, define the left hand and the right hand side of the J dual constraints. The dual objective coefficients equal the right hand side of the primal, so that's what we just did. So we did the objective function. Now we're going to do again, are going to use those coefficients in the yellow colors. So this The coefficients for this one is 1, and this is 2. So this is going to be 1 times y1 plus 2 y2. And then the right-hand side is 5. As we saw here in this table, the constraint type, since you're going from maximization to minimization, the constraint type of the dual is going to be greater or equal to. Okay, so this constraint is going to be greater or equal to. And that's my first constraint. I'm going to repeat the process with all the decision variables of the original problem. So now I have 2y1 minus 1y2 greater or equal to 12. Yes, so this coefficient is my right-hand side. This is y1, this is y2. So 2y1 minus 1y2 greater or equal to 12. Now I'm going to look at my third constraint. This is y11 plus 3y2 greater or equal to 4. And then finally, I have 1. This was 0. And then this is 0, 2. So what this is going to state is 1y1 plus 0y2 greater or equal to 0. In terms of my design of my decision variables, in this case, y1 and y2, we go back here, the variable sign is going to be unrestricted. So what that means, based on the rules, is that y1 and y2 will be able to assume positive and negative values. In this case, they're unrestricted. But if you see in this case, this decision variable or this constraint basically is telling you that y1 is going to be greater or equal to 0. So only y2 will be unrestricted inside. So y1 is going to be greater or equal to 0 because of this constraint. But the rest they have already. Say that again.
I mean, the rest you can not say they are restricted if they have bigger than or equal to 5.
Yes. But those, I mean, what I'm trying to say is, you remember in every formulation, we always stated the sign of the decision variable. So that was the last step. So we typically say, okay, y1 or x1, x2, and x3 will be greater or equal to 0. Typically, that's what we are going to do when we are formulating our original models, right? We want, most of the time, we want our decision variables to be greater or equal to 0 or positive. That's the case of this problem. Okay, we are formulating the original problem. They have x1, x2, and x3 greater or equal to 0. But when we formulate the dual, that's no longer the case. Okay, if we are formulating the dual for this problem, the decision variables are going to be unrestricted in sign unless there is a constraint that is telling you the other ones. So in this case, there's a constraint that is built by this last decision variable in the original problem. When you build that constraint, you're going to end up having a y1 greater or equal to 0. So that's telling you right there that y1 is going to be positive. We don't have a constraint like that one for y2. Y2 is embedded in the other constraints, but it's not a specific constraint telling you that y2 will be greater or equal to 0. So for this problem, y2 will be unrestricted. Okay. Good. So let's try the other one. I'm going to let you work on this one by yourself for a few minutes, and let's see how far you can go, and then we will discuss it. So I'm going to give you 5 minutes to try this, or maybe less, 2 or 3 minutes. I want you to formulate the dual for a problem, a minimization problem. I have given you already the standard or the equation form, and you need two dual variables. So you basically have to repeat the same process. I already did that for this one. In the dual, yes. So you have to consider the slacks and the x's as part of your dual formulation, like we did here. X4 is the slack, so X4 is defining this last constraint.
No, I'm talking about like going from this.
Oh, for this one?
Yeah, so if you want to solve it.
Oh, yes, you wouldn't have to put that into standard form. Yes. Yes, yes. But we are not there yet, but that's right. That's correct. Now I'm just interested in knowing if you can formulate the dual from a original problem. Okay, so let's try this one. So we start with a minimization problem. So the dual will be a maximization problem. This is max. And then we're going to use the coefficients of the right-hand side to build our objective function. And we're going to multiply those coefficients by the dual variables. So in this case, we had 3y1 plus 5y2. Any questions about that? Good. Okay, so now we transition to the constraints, and we're going to use the coefficients of each decision variable to formulate our constraints. So if for the left-hand side of the constraints, we're going to use the coefficients of the left-hand side of the original problem. So we have 1 y1 plus 2 y2. And then since we are maximizing, we're going from minimization to maximization. Now the sign of the constraint is going to be less than or equal to. And the right-hand side of the constraint is the coefficient of the objective function. Any questions? Good. So we're going to repeat this process. Now we're going to look at the coefficients of the second decision variable. So we had 2y2 minus 4, I'm sorry, y1 or y2 less than or equal to 12. And then we have minus 1 plus 0, minus 1 y1 plus 0 y2 less than or equal to 0. And then we have 0 plus 1 less than or equal to 0. So again, we typically will force our decision variables in the dual problem to be unrestricted. But if you look at those two constraints at the end, this can be converted to y1 greater or equal to 0 by dividing by -1. And this one is telling you that y2 will be less than or equal to 0. So those are your bounds for your decision variable. Any questions? Okay, so the third example, this is a case in which we have one of the decision variables to be unrestricted. And if you remember earlier this semester, we have a modeling technique or trick to represent these unrestricted in sign decision variables like x1. So for the original problem, we have a maximization problem, 5x1 plus 6x2, and then 3 constraints. And we have one of the decision variable that is unrestricted in sign. So that means that x1 can be positive or negative. And then we have x2 greater or equal to 0. So if we want to set up this problem into equation form, you remember that we have this substitution. So we are modeling x1, which is unrestricted in sign, with 2 variables now. One that assumes negative values and one that assumes a positive number. And that modeling, we basically have this substitution into the original problem. So everywhere we have x1, we are going to add this, or we're going to insert this substitution. So that standard form of the problem is what we have here in the second column. So we have a excess variable for the second constraint, and we have a slack variable for the third constraint. So in this problem, we have 3 decision variables. I'm sorry, 3 dual variables, because we have 3 constraints. We're going to proceed in the same way. We have a maximization problem that we are going to make a minimization problem. And we're going to use these coefficients to formulate the objective function. So this is 5 y1 plus 3 y2 plus 8 y3. And then for each one of the decision variables, we're going to have a constraint. So for the first constraint, we have y1 minus y2 plus 4 y3. And this is greater or equal to 5. For the second constraint, we have minus y1 plus y2 minus 4y3 greater or equal to minus 5. And then we have 2y1 plus 5y2 plus 7y3 greater or equal to 6. Minus y2 greater or equal to 0, y3 greater or equal to 0, and y1 will be unrestricted. Okay. If you look at the constraint, first and second constraint, there are the same in terms of coefficients. Actually, if you multiply the second constraint by -1, you get something like this. You multiply this constraint by -1, you get the following. You get y1 minus y2 plus 4y3 less than or equal to 5. So if you look at this constraint now and this one, they're the same. The only difference is the sign. But if you look, they are only overlapping on that equality, right? So it's basically saying this constraint, let's say this is the equality. So one of the constraints will be going in this direction and one of the will go in this direction, and they will meet in the equality sign. So we can, if we understand that, we can basically substitute these two constraints by one constraint, in which you're going to have the same coefficients, but instead of being one constraint greater or equal to 5 and one constraint less than or equal to 5, you will have only one constraint in which it's going to be equal to 5. Because that's the only point in which this constraint is, these two constraints will be able to meet. Okay. So just for as a summary of constructing the dual problem, this is the summary. So rules for constructing the dual problem: if you have a maximization problem, you're gonna change that problem to a minimization problem. Greater or equal to constraints will give you variables that are less than or equal to 0. Less than or equal to constraints will give you decision variables that are greater or equal to 0. And equality constraints will give you unrestricted inside decision variables. If your variables are greater or equal to 0, then your problem is going to have a greater or equal to 0 constraints. Your decision variables are less than or equal to 0. For the original problem, the variables are going to be less than or equal to 0. And if you have unrestricted decision variables, then your constraints will be equalities, which is what I just showed you in that last example. Okay, so if the primal is maximization, then we saw that the dual is a maximization and minimization and vice versa. Okay, so now we understand the formulation of the dual problem. Let's look at the relationships between these two models. So again, as I mentioned, if you solve one of them, and if you solve both of them, you'll get the same objective function value. So at the end, you're going to get the same solution. Decision variables are going to be different because you still get the same objective function value, but the decision variables are going to be different in value because they're going to represent different things. But if you get the decision variables for one of them, you can obtain the decision variables for the other without having to solve both problems. So let's talk about those relationships. Changes made in the data of an LP model can affect the optimality and or the feasibility of the current optimal solution. This section discusses primal dual relationships that can be used to recompute the elements of the optimal simplex Tableau. These relationships form the basis of for the economic interpretation of the LP model or linear programming model and for post-optimality analysis. So everything that we are doing at this point with the sensitivity analysis and the dual theory and the dual concepts is after you solve the problem, can we get some additional insight, post-optimality analysis. So the simplex Tableau layout, the figure represents the starting and the general simplex Tableau schematically. Okay, so in the starting Tableau, the constraints coefficients under the starting basic form or the starting variables form an identity matrix. Okay, and this is something that I have mentioned several times. So when you set up your initial Tableau, the starting variables or the basic variables, you can identify them by the identity matrix, right? So those are your basic variables. Those are the ones that are going to give you the initial solution for the problem. And this is the starting tableau. After performing an iteration, that area where the identity matrix was at the beginning, that location where the starting variables were, are now creating what we call the inverse matrix. Okay, so that inverse matrix is going to contain some information that is important for us because it's going to allow us to gather some additional insights from the solution. So that's what I want you to keep an eye on. So remember, if we have less than or equal constraints, we were having here the slack variables, and those slacks were generating these identity matrix. So that identity matrix is going to now contain some additional information as we move forward into solving this problem. So let's say you're getting into a general iteration. So this could be iteration 1, 2, or 3. If you look at the same location of where the identity matrix was, that's going to be the inverse of the solution. Subsequent iterations of the simplex tableau generated by the Gauss-Jordan row operations modify the elements of the identity matrix to produce what is known as the inverse matrix. The inverse matrix is key to computing all the elements of the associated simplex tableau. So in terms of the dual solution, the primal and dual solutions are closely related. As I mentioned already, you solve one problem, the solution of the other one can be obtained from the solution of the other one. The optimal solution of either problem yields the optimal solution to the other. In an LP model in which the number of variables is considerably smaller than the number of constraints, computational savings may be realized by solving the dual. Okay, so that's what I mentioned at the beginning as well. So if you have a problem that is computational challenging, and it's taking you like an hour, 2 hours to be solved, solving the dual may save you some time in terms of computational solution time. So solving the dual may be an alternative for you to get a solution faster. Why is that? The amount of simplex computations depends largely on the number of constraints. So if you have too many constraints, then it will take you longer to solve the problem, even with a computer. So if you can reduce the number of constraints by formulating the dual, then you can save some computational time. This section provides two methods for determining the dual values. So for example, if you have the solution of the original problem and you want to know the solution of the dual problem, these are two methods for obtaining the solution of the dual. So for example, method 1, the optimal value of the dual variable yi is going to be equal to the optimal C coefficients of the starting variable xi plus the original objective coefficient of xi. Method number 2, the optimal values of the dual variables are going to be equal to the row vector of the original objective coefficients of the optimal primal basic variables times the optimal primal inverse. The elements of the row vector must appear in the same order the basic variables are listed in the basic column of the simplex tableau. And this is very important. I'm going to do some multiplication of matrix or vectors times the inverse, but we have to keep an eye on the order of decision variables, meaning that if you set up your problem in the Tableau and you have, let's say, x1 in the first row, x3 in the second row, and x5 in the third row, when we set up these column vectors, we have to make sure that the order inside the elements of the vectors are following the order of those decision variables column. So that's what this is trying to say. The elements of the row vector must appear in the same order the basic variables are listed in the basic column of the simplex tableau. I'm going to see this with an example. So let's consider this example. Okay, so this is example 4. We have a maximization problem in which we are trying to solve and find the optimal solution of the dual. So in this problem, I'm formulating this in into the standard form, right? And if I were to solve this by hand and I need to find an initial solution, in this case, I'm applying the M method, right? So I need an artificial variable for the second constraint. So for the first constraint, I have a slack X4. For the second constraint, since this is an equality, and I need to find an initial solution, I can apply the simplex method, the M method, the big M method, or the two-phase method. In this case, I'm using the big M method. So I'm adding an artificial variable to that second constraint, and I am subtracting that artificial variable in the objective function, right? I'm penalizing the objective function with this artificial variable. So this is my primal in equation form. The dual of this problem, following the same steps, we're going to minimize and then we're going to use the right-hand side coefficients, 10 times y1 plus a times y2. And then this is going to be subject to, going to look at the coefficients of each decision variable now. So this is y1 plus 2 y2 greater or equal to 5. Have 2 y1 minus y2 greater or equal to 12. Y1 plus y3 times y2 greater or equal to 4. And then the next one is going to be for x4. So this is y1 greater or equal to 0. And then I have y2 greater or equal to minus m. And m, remember, is a very large number. A large number in this case could be 1,000, 1,000, or 500. 100 will be enough too, because it's large enough. So the idea now, I have the dual problem, and I want to apply these two methods so I can find the optimal solution for this problem in terms of y1 and y2. Okay, so on the next slide, I have the optimal tableau for the original problem. So the original problem optimal solution is depicted by this tableau. So the optimal solution for this problem, the primal. Okay, so the optimal solution for this problem, I have the final solution after implementing the simplex method. This is the optimal solution of the problem. Okay, so this is telling me that x2 equals 12/5, and that x1 equals 26/5, and that the optimal solution for this problem is 54/5. Okay, so now I want to find the solution for our dual variables. So what will be y1 and what will be y2? Okay, so remember in the original problem, we go back here, this will be our, in the original problem, the identity matrix in the first iteration is telling us that the basic variables, which are the basic variables for a problem. So in this problem, in the first tableau, for this problem, the basic variables in the first tableau will be the slack and the artificial variable. Okay, and I need to know that because I'm going to use those two variables to help me find the dual values of the dual problem. So in the initial solution, remember, in the initial Tableau, my basic variables are located where the identity matrix are. So in this case, for this problem, those are going to be the slack variable and the artificial variable. So that's why my starting primal basic variables are x4 and the artificial variable. So that's why I'm listing them here, because those are the ones that are going to give me are going to help me find the original or the optimal solution for the dual problem. So what are the z equation coefficients for these two? If you look at the optimal Tableau, the z optimal coefficients are 29/5 and -2/5 plus m. Okay, so those are the coefficients that are going to need. And this is again for method 1. Method 1 says that the optimal value of the dual variable, yi, is going to be equal to the optimal primal z coefficients of the starting variable. So those are the ones that I just highlighted, plus the original coefficient of xi. So the z equation coefficients in the optimal Tableau are this and this. So this is 29/5 and -2/5 plus m. The original objective coefficient. So now I have to go back to the original formulation, and the original coefficients are here. For those two decision variables, the original coefficients are 4 and -m. So the original objective coefficients are 4 and -m. The dual variables associated with each of them are going to be y1 and y2. And the optimal dual values, going back to this, the optimal dual values are going to be the optimal primal z coefficient of the starting variable xi plus the original objective coefficient of xi. So I'm going to do that operation here. This is going to be 29/5 plus 4. I'm sorry, this is not 4. Yeah, I'm sorry. This, I got confused. So we don't have a coefficient for x4, right? So in the objective function, x4 is 0. So the coefficient for x4 should be 0 instead of 4. My bad. Because this is for x3. So what we have here in this is plus 0 times x4 minus mr. So in this piece right here, this is the coefficient for x3, not x4. So that's incorrect. This should be 0. Okay, so now I'm doing the operation. This should be 29/5 plus 0. So this is 29/5. And then this one for y2, we have -2/5 plus m minus m. So this is equal to -2/5. So in conclusion, optimal solution for the dual is y1 equals 29/5 and y2 equals -2/5. So by using the information that I have about the original problem, I'm able to solve the dual problem. Okay. So that's using method 1. We're going to employ method number 2 now. Yes, go ahead. Yes, and remember this is a number. So in this case, I'm not using a number. Yeah, so this could be 100. Yeah, so in this case, it will be canceled out by itself. Yeah, yeah, yes.
So we're looking for the for R, you pull it from the constraint or from the
Which one?
so for R you can make it down, but it also has a coefficient of 1 and like the constraint.
Oh, yeah, so this is the original objective coefficient
Oh, from the objective function.
from the objective function. Yes, so that will come from here.
So we don't care that like there's a 1 from the R the second constraint.
Here, no, because we are looking at the objective function. Yeah. And remember, this is method 1. So we look at the optimal primal z coefficients of the starting basic variable, and we add that to the original objective coefficient of x1. So the optimal primal z coefficients of the starting variables, those are given here, 29/5 and -2/5 plus m. And then we add that to the original coefficients of the primal model. Method number 2, we're now going to use this. We're going to get the same solution. You'll see that it's going to be the row vector of the original objective coefficients of the optimal primal basic variables times the optimal primal inverse. Remember that for this, the elements of the row vector must appear in the same order of the basic variables are listed in the basic column of the simplex tableau. So I'm going to show you what that means now. So for this method number 2, we have the optimal inverse matrix highlighted in the Tableau. Under the starting variables. X4 and R is this 2/5, 1/5 minus 1/5, 2/5. Okay, so if we go back here, this is what I'm referring to, and I apologize. There's a, so this should be 2/5 here. Okay, so this is the matrix that I'm referring to. So that's where the original identity matrix was located. So that's where the inverse is going to be located, in the same area where the original identity matrix was located. So in the optimal Tableau, the inverse will be located in that area. So I'm pulling that matrix from the Tableau, and that's the inverse matrix. Okay. The next thing is the order of the optimal primal basic variables in the basic variables column is x2 followed by x1. So if you go to this Tableau, which is the optimal solution, this is what I'm referring to. In the optimal solution, you have x2 and then x1. So the order of the optimal primal basic variables in the basic variables column in X is x2 followed by x1. Then the elements of the original objective coefficients must appear in the same order. So the original objective coefficients will be equal to coefficient of x2, then the coefficient of x1, so in this case, this is going to be 12 and 5. So go back here. This is what I'm referring to. I'm using the original coefficients of the objective function, but they have to appear in that row vector in the same order as you are presenting them in the basic solution for the optimal Tableau. Okay, so if we go here, the order is x2 followed by x1. So now I'm going to pull the objective coefficients from the original objective function, but I have to use them in the same order. So for x2 goes first, so it's 12, and then the coefficient for x1 is 5. So in my row vector here, I'm going to have 12 and 5. And that's the most challenging part for method 2. If you can get that right, then the rest is very simple. You just have to use the inverse. You know where the inverse is located, so you're going to use the inverse matrix. So the optimal dual values y1, y2 are going to be equal to 12, 5 times the inverse, 2 over 5, 1 over 5, minus 1 over 5, 2 over 5. And this is going to be equal to 29 over 5 minus 2 over 5, which are the same values that we obtained with method 1. Okay. So 2 methods. I have the original model, my linear programming model, the original model. I can solve the problem using the original model, and I have an optimal solution for the original model. And use that optimal solution of the original model to get the solution of the dual, which is what we are trying to do. Okay, so you'll see why this is important. Okay, so for now, I'm just getting you into the technique of getting the solution. But then on Wednesday, we're gonna go deeper in terms of why is this important, how this connect, why is this true. If you plug in these values, 29/5 and -2/5 into this objective function, you should get the same solution in terms of the objective function, 54/4/5, which is what this is trying to represent. But we'll see how time. So let's look at this. So the primal dual objective values for any pair of feasible primal and dual solution, the objective value in the maximization problem is always less than or equal to the objective value in the minimization problem. At the optimum, the relationship holds as a strict equation, meaning that the two objective values are equal. So if you have an original problem, linear programming model, you're maximizing and you're minimizing the dual, the optimal solution will meet in the middle and it's going to be the same. Okay, so solving one problem will give you the same objective function for the other one. But the decision variables are going to be representing something different. Okay, and we're going to talk about that on Wednesday. Okay, so the economic interpretation of the duality. Any questions? Yes. Yes. This one? I mean, why do we use this? X4 and R, because those are the ones giving you the initial solution for the problem. So when we start, if you remember here, they're starting variables. If you go back to when we started with the simplex method, less than or equal constraints, we were using the slack variables, and you always have that identity matrix under S1, S2, and S3, the slacks, right? Those were giving you the initial solution for the problem. Okay, but later we added the artificial variables for other type of problems. But I want you to remember that one because I think that will be the easiest way to understand it. So what we want to do is we want to keep an eye on the location where the starting variables were placed in the Tableau. That location of the starting variables, S1, S2, and S3, will be under the identity matrix. And I always told you, if you want to find the basic variables, you have to look at for the identity matrix, right? So for the first Tableau, we have the identity matrix, and those were connected to the basic variables here, right? So what I'm telling you now is, if you understand that you were getting the initial solution using these starting variables, now where that identity matrix was located, now you can use that information to do other things. Okay, so we are using those variables because the matrix that is generated where the identity matrix was is called the inverse, and that's containing the information that you will need to do this post-optimality analysis. So in general, basically, what we are forcing us to use those variables because they are connected to this inverse, which is what we are using to generate this optimal solution for the dual now. That's the inverse. And that inverse is where the original identity matrix was located. I don't know if that answers your questions. Yeah, okay. Any other question? Good. So on Wednesday, we're going to continue our discussion. We're going to look at the economic interpretation of this duality, and I'll see you on Wednesday. Yes, because the homework is connected to the previous lecture. Yes, sensitivity analysis.
Oh.